Okay, so question 63, indicate which or whether each of the following pairs of compounds are identical, enantiomers, diastereomers, or constitutional isomers. So before we even begin, you need to really have a very good idea of what these four definitions really mean to be able to even use them to try to separate these different questions. So there are actually, I think, 8 questions for this, question 63. And I'm not going to do them all, but what I will do is I'll do these 3, and then after that you should be able to figure out the other ones pretty easily, I think, because each one are little small variations on these main questions. So, alright, so we have this question A, or sub-question A, this 3-membered ring. So there's a couple different ways you can go about this. So first off, let's see if these guys are constitutional isomers or identical. Those are pretty easy to tell right away. So for the constitutional isomers, you need to remember that this is talking about connectivity. So if you have same atoms, so if the molecular formula is the same but the atoms are attached in different positions, that's when you have different constitutional isomers. So connectivity is the big issue here. So we can check that really easily. So 1, 2, 3. If we start numbering our 3-membered ring, 1, 2, 3, you can see that overall we have the same number of bromines. 2 here, 2 here, 2 hydrogens there, 2 hydrogens there, 2 there, 2 there, and 3 carbons. So overall the molecular formula is the same. Then the question is the connectivity the same? And in this case, it's very easy because no matter how you really arrange it, you can't have a bromine, really too far away from the other. So theoretically, you could have this bromine attached to carbon 1, and then definitely, yes, you would have a constitutional isomer. But in this case, for both of these, compounds, you have a bromine on carbon 1 and a bromine on carbon 2, 1 and 2. Okay, so the connectivity for this one at least is the same. So we have the same connectivity. So it's not going to be a constitutional isomer. So then going back to the easier question again is identical. So are these compounds identical? So there are 2 things you need to check for. One is the constitutional isomer criteria. And then 2, if you don't have a constitutional isomer, you might have some other type of isomer in terms of regiochemistry. Okay, so that would be some kind of configurational isomer. So what we're going to do is see if you have the same kind of configuration for each of the attachment points. So it looks like for this first one we have hydrogen going backwards and forwards, and for this one right here we have a hydrogen going backwards and another hydrogen going backwards. So it's pretty obvious that you have this trans relationship between these 2 hydrogens and a cis relationship between these 2 hydrogens. So you can't really call them identical because they're going to be different in a 3-dimensional sense. Also, what makes this really important is the fact that this molecule, you can't have full 360-degree rotation along this bond right here. So you can't do that. And so no matter what, you're going to have these 2 hydrogens either being cis or being trans to each other. So we're not going to have any kind of identical relationship between these 2. So the only 2 that we have left over is the enantiomer possibility or the diastereomer possibility. So the way we're going to go about it is you can go about it 2 different ways. One is by formally assigning R and S to each of the chiral centers, and after that you could try to rotate these guys in your mind. And I'll try to do both of them. And some people might think one way is easier, some people might think the other way is easier. So either way that works for you is totally fine. So thinking about priority for this guy right here, hydrogen is always going to be the lowest priority, so that's number 4. Bromine is the highest molecular, or is the highest atomic number between bromine, carbon, and carbon, so this is going to be number 1. And then here you have to choose between this carbon right here and this carbon right here. So this carbon right here has 2 hydrogens and this bit, and this hydrogen, or this carbon right here, has a bromine, hydrogen, and this other bit of the 3-membered ring. So the highest priority on this carbon is going to be this bromine. Highest priority on this carbon is going to be this carbon. Okay, so bromine is going to have a higher atomic number than the carbon. So this group right here, this carbon, is going to be the 2nd highest priority. And then followed by this carbon right here. This is going to be the 3rd. highest priority. So we already know that this hydrogen is in the back, as our convention has told us from class. We need to have our lowest priority pointing away from us. So now we can say that this carbon right here is going to be in an S configuration. So overall S. Okay, so we can go ahead and get rid of this stuff just to make it a little bit simpler to see. Okay, so go ahead and get rid of that right there. Okay, so now what we could say is we could formally figure out the R and S for this carbon, or we could ask ourselves if it looks like it's a mirror image. And if it's a mirror image, then we know we're going to flip R and S here because we have the same groups attached. So we have a bromine, hydrogen, and CH2 for this chiral carbon, and we have a bromine, hydrogen, and CH2 for this chiral carbon. So everything else is being held constant. So we can do this little quick way of figuring it out. So, you know, if we had this mirror, hydrogen would be in the back, bromine would be in the front, and since it's a mirror image, we would have to flip R or S to R. But since we don't have that, then that means that this guy must also be an S. Okay, so that's the quick way to do it. Let's do it the fast way or the slow way. So the slow way is again to look at the bromine. Bromine's number 1, hydrogen's number 4, and for the same reasons as before, this carbon is going to be the second highest priority, and this carbon right here is again going to be the third highest priority. So again, we have our highest priority or our lowest priority not pointing in the back. So you can either do a single swap rule, or you can kind of look at it from a different perspective, have a little eyeball coming from the back. Okay, so if you did the eyeball coming from the back like this, looking at that carbon, you'd see this 1, 2, and 3. And if you have to position yourself to where the hydrogen is going to be behind everything, so it's going to be an S. Okay, so let's do that in more of a single swap kind of way. So let's go ahead and do the single swap rule for this guy. Okay, so I'll redraw this a little bit more formally. And what we're going to do is we're going to switch this hydrogen for the bromine. So the hydrogen is going to be in the back, bromine's in the front. This is just a CH2, HBr. Okay, so now in this case again, 1, 2, 3, 4. So 1, 2, 3. This is R, and again, this is a very easy mistake to make, is that if once you do the single swap rule, students will make the mistake of saying that because this center is an R, this center is also an R. But that's not correct. Remember that after you do the single swap rule, you have to go back and switch the configuration designation. So since this is an R, this must therefore be an S. Okay? So that's the two ways you can do it. You can either do it the fast way, which is position yourself, you know, your virtual self behind this carbon, have it pointing away from you, and see these lining up 1, 2, 3 in a S configuration. Or you can do the single swap rule, pull it over here, see that this is an R, this is an R, this must be an S. Okay, so this guy, this three-membered ring is an SS configuration. So then we can look at this other compound right here, and again we can do our priorities, doing all that, or you can just look over here and just kind of pirate the work you've already done. So this chiral center right here is the same as this chiral center, so it's going to be the same overall SR configuration. So this is going to be S. And this chiral center right here is actually switched, basically doing the single swap rule that we've already done down here. So if this is S, this must be R. Okay, so now we have to go back to our definition of enantiomers versus diastereomers. If this was an enantiomer, then it would be a non-superimposable mirror image. If it's a mirror image, that must mean that all the chiral centers configurations are switched. So if we look at the left, that three-membered ring, SS, for the compound on the right over here to be an enantiomer, both of these would have to be RR. So since we've only switched one, we switch this rightmost carbon, this carbon right here, from an S to an R only, then we're going to have a molecule that's still going to be non-superimposable, but it's also going to be not a mirror image. So this is the perfect definition of a non-superimposable, non-mirror image. So that makes this compound right here a diastereomer. Okay. So we have a diastereomer right here for these two guys. Okay? So now what I'm going to do is go on to sub-question D. I'm going to do the exact same thing, but I'm going to do it in a little bit faster fashion. So let's just look at these two cyclohexane molecules. Again, let's see if they're constitutional or not. If they're constitutional, then the positioning will be different. So the positioning here is 1, 2, 3, 4. Just kind of a random arbitrary numbering. 1, 2, 3, 4. So the positioning is exactly the same. We have the same number of atoms. So these are not going to be constitutional isomers. The connectivity is exactly the same, and the molecular formula is exactly the same. So they're also obviously not identical because their three-dimensionality is different. So if you look at carbon 3 and carbon 1, carbon 3 and carbon 4 are both pointing up and down respectively, and carbon 1 is pointing down in this case and up in this case. So the three-dimensionality is not the same, so they are not going to be identical. So that leaves us with either an enantiomer or diastereomer. Okay. So what we need to do is we can either go through all this hoopla of trying to figure out the single swap rule and figuring out R and S, or we can just kind of look at it and see, well, what if this was an S? If this is an S, then this must be an R. I have no idea if that's right or not, but if it was an S, this is an R. If this is an S, then this is an S. And if this is an R, then this is an R. And again, I have no idea if the R's and S's are the same, but this is just to kind of illustrate a point. So these two chiral carbons, or these two chiral centers, will retain the same configuration. If this is an S, then this is an S. This one right here on carbon 1, however, will be totally different. If this is an S, then this will be an R. So what that must mean is that we are switching only the configuration of one of the three chiral carbons. And going back to our definition of an enantiomer, so that means if we have an enantiomer, we have a mirror image. If we have a mirror image, then we have the situation where we'd be switching the chirality or the chiral configuration of each of the carbons. So if this was SSR for this guy, in order to have an enantiomer, we would have to end up having another molecule that was RRS. So since we don't have RRS, that must mean that these two are not enantiomers, they must be diastereomers. So these are also diastereomers. Okay. One thing to look out for here is the possibility of rotation. So you could always possibly rotate these molecules and try to get them to lock in place. Because it may look like this is 1, and this is 3, and this is 4, 1, 3, 4. Sometimes whenever you have internal symmetry like this, straight through right here, you can have some funky things going on. But just be careful about possible rotations. And so this caution is actually illustrated perfectly right here. So if you look at this other subquestion H, going back to our definition of enantiomer. So the enantiomer would be a mirror image, and if you draw a mirror right here between these two molecules, it looks like you have a perfect mirror image between all of these different groups right here. So one thing you want to make sure of whenever it does look like you have a mirror image is to make sure that you can't just flip everything in some way, shape, or form. Like you can't rotate or translate the molecule in 3 dimensions, or rotate it along the plane of the paper, just to make sure that it doesn't actually fit. So what we can do is actually test this enantiomer definition to see if it checks out. So what we're going to do is we're going to take this this molecule B, I'll call this guy molecule A, and what we're going to do is we're going to do a rotation. We're going to do a rotation along the y-axis, so right here, it's the x-axis. So we're going to rotate like this, okay, and we're going to rotate 180 degrees. So if we rotated 180 degrees, this is what the molecule would look like. Okay, so now if you compare and contrast this molecule with the other molecule on the left, it looks as if it is a perfect fit. Other than the slight differences in geometry and the way that I drew them, the connectivities are exactly the same. So the connectivities are exactly the same. So it can't be a constitutional isomer, which, again, going back to the definition, if you have a constitutional isomer, the connectivity is going to differ. But also, we have this issue of not having any differences in the three-dimensionality of the molecule. So in this case, no, these are not going to be enantiomers because you can actually have a superimposable image. Okay, so going back to the definition of an enantiomer again, the enantiomers are going to be non-superimposable mirror images of each other. So just because you can make something have a mirror image doesn't mean it's an enantiomer. So if it looks like it has a mirror image, try to rotate it a little bit and make sure that you can't actually superimpose. Okay, so in this case, this molecule is exactly the same as this molecule. So in this case, we actually have a molecule that's identical. Okay, so there are another 3, 4, 5 questions just like this in sub-question or in question 63. Try to go through them all and try to do an intuitive analysis first and see if you can back it up by doing some kind of rigorous RS configuration analysis. If you have any questions, feel free to chat with me and we can go through any issue that you might have with any of these other questions. Okay, good luck.